Hello everyone, I am Abhijeet Sansare and my colleague Pritam. We are here to give you some useful information about SoC memory system design. And these are the content which we are going to cover in this session. The contents are memory technology, in which off-chip memories and embedded memories. Next topic will be discussed by my colleague Pritam, which is a memory optimization and management, in which he is going to cover reordering and remapping, transition reduction of memory buses, reduction in memory size, dynamic power management, and constraint aware target for memory system. As the increasing integration density of various IPs into SoC, the memory system becomes a dominant role to determine the final performance area and power consumption of SoC. The memory system design involves various aspects, from bottom level on chip or off chip memory technologies to the high level memory optimization and management. The embedded memory now is driven by the SoC and thus becomes more integration friendly, either at the interface or at the process technologies. Memory optimization and management optimizes the memory access by high level recording, remapping, and memory size compression. Power of the memory system can be further reduced by transition reduction of memory bus and dynamic power management of memory system. Further optimization of memory access needs the memory controller to fully utilize the available bandwidth. The optimization of memory system is part of complex SoC design problem, which can only be analyzed and solved within a target system. Recently, multimedia and wire or wireless communication technologies have fundamentally changed the way we create, communicate, and consume audiovisual information. These technologies have not only transformed existing applications and services like the distribution of entertainment video to the home, but also spawned brand new industries and services like video conferencing, direct-to-home satellite distribution, digital video recording, video on-demand services, high-definition TV, video on mobile devices, streaming video, etc. The realization of this application relies on VLSI for cost-effective implementation. The memory technology. Today's consumer electronics products process massive amount of data for audio and video and other applications. Thus, it demands variety of memory devices and memory size to work together, from volatile dynamic RAM for runtime storage and non-volatile flash for massive data and program storage. As the devices become portable, specialized low-power memory such as mobile pseudo RAM, SRAM, or mobile dynamic RAM emerges to support these battery power applications. Besides, as the target application of the embedded system diverges, the memory requirement are also diverse. Graphics chip favor streaming. If the memory size demand is small enough, several megabytes embedded memory can provide another high bandwidth solution that off-chip memories cannot offer, which is a solution that current high bandwidth demanded graphics chip or video encoded adopts. The discussion will more bias to RAMs instead of ROM or flash, since they store the time varying data and thus significantly affect the overall area, speed, and power. Off-chip memories. Traditionally, dynamic RAM roadmap is largely driven by the PC products. This mainstream PC favored DRAMs constitute more than 90% of total production, achieving the lowest price per MB, and thus widely supported and used in the other domains. Most of the modern dynamic RAM development is based on SDRAM. A typical SDRAM accesses the one data at the positive clock edge. To improve its throughput, DDR SDRAM enables 2 instead of 1 data prefetch for 1 bus cycle by adopting double clock edge data sampling. Thus, the data transfer rate of DDR is twice of that in the SDRAM. Furthermore, the latest DDR2 SDRAM enables 4n prefetch in contrast to 2n prefetch realized in DDR. It means in fact that each memory bus cycle DDR2 transmit 4 bits of information from logical memory chip banks into input-output buffer using one data interface line. This makes DDR2 SDRAM be able to provide quadruple bandwidth than SDRAM with the same core operating frequency. The overall operating voltage is also reduced from 2.5 volt to 1.8 volt to save the power consumption and allow higher frequency operation. For high bandwidth application, DDR2 SDRAM will be suitable solution. The new development of DRAM improves the burst bandwidth. Thus, how to select the proper DRAM types for the SoC system depends on the application needs. For streaming applications like video and audio processing, conventional dynamic RAM is quite suitable. However, for the latency sensitive applications like networking, low latency dynamic RAMs can satisfy both the latency and bandwidth needs. For mobile application, low power consumption becomes one of the major concerns. SRAM has been choice since it does not have a leaking per cell charge storage capacitor that requires periodic refreshing and draws the standby current. However, as more and more functions are squeezed into the system, the required amount of code and data storage also increases exponentially. Thus, the cost per bit advantage of the DRAM over SRAM becomes apparent. To address both needs, size and power, specialized low power memory like mobile DDR SDRAM or pseudo SRAM have been developed. Mobile DDR SDRAM incorporates several low power functionalities into DDR SDRAM to reduce the standby current. First, the supply voltage is reduced to 1.8 volt from 2.5 volt, providing half of the power reduction. Second, it now can support partial array self refresh, only half or one-fourth instead of whole dynamic RAM array. Thus, only the array with the valid data will be refreshed to avoid unnecessary self refresh current. To further reduce the self-refresh current, it also lengthens the refresh period for lower temperature, called temperature compensated self-refresh. Pseudo RAM, as its name suggests, combines advantages of the low cost dynamic RAM cell and the simple traditional SRAM interface non-multiplex address bus. The integration of the off-chip memory is divergent from system on-board level to the system in package level. Traditional system on-board level integration has its advantage of well-established practices for years, including chip testing, assembly, and board testing. Embedded memories. With the VLSI technology stepping into the deep submicron era, hundreds of millions of transistors can be integrated into the single chip. Though more logic can be integrated into the chip, however, most of the transistors go to the memory, ranging from half to the estimated 90% of the silicon real estate. According to the ITRS, embedded memory brings a lot of benefits but may not be cheaper and naturally coexist with the other logic on the same chip. Embedded memory offers the major benefits of low power, high bandwidth, high speed, and enhanced flexibility, and the side effect of minimal board space and increased reliability. When the memory is integrated into the chip, all the high loaded and limited off-chip interconnection are replaced by a small loaded and almost unlimited on-chip communication. Thus, the power consumption and performance are improved significantly. This wide bandwidth is specifically useful and attractive for bandwidth demanding applications like video and graphics, a major user for large embedded memories. However, how to integrate this embedded memory with the other logic circuits requires trade-off on process compatibility and performance. Logic and memory are fundamentally different technologies with the sometimes contradict demands, from the interconnection requirement to the cell structure. Logic usually scatters across the chip in an irregular fashion and requires more metal layers, 6 or more, for interconnection, while memory array is more symmetrical and repetitive, requires far less interconnection than logic. On the other hand, standard memory process require 4 or more polysilicon layers for floating gate of EEPROM, EEPROM, and flash memory, the register of the 40 SRAM cell, and the stack capacitors dynamic RAM cell, while logic process usually uses 1 or 2 polysilicon layers just for transistors. An extra metal or polysilicon layer add cost, complexity, and fabrication time. All of these issues have to be considered and clarified for integration. In general, the integration approach can be classified into two approaches: logic process compatible embedded memories and dedicated process embedded memories. Commonly used to logic process compatible embedded memories are ROM and 60 SRAM. ROM cells are much smaller than RAM cells. Due to its read-only feature, its application is also limited to permanent lookup table or programs. Dedicated process embedded memories usually add the extra processing step for memory fabrication into the logic process. The required steps depend on the targeted memory technology and design. Embedded non-volatile memories have attracted many applications in modern SoCs. They provide non-volatile storage for frequently read but rarely written configuration information. However, the embedded non-volatile memory still adds the process complexity by the introduction of the floating gate for the charge storage and retention, high voltage transistor, as well as design for routing the required high voltages to the memory array, and the complexity of decoding, sensing, timing circuits, and the algorithm stored in the state machine. Disregarding the underlying process, the integration of the embedded memories is still a problem since the large area blocks will impose large blockage areas that place and route tools must detour around to connect the input output and core logic areas. To be SoC friendly, integration and with the aid of the multiple level of metal layers, the latest embedded memories allow active signals to pass over the macros, and thus the router can take the shortest path between the input output and core areas. This helps the layout designers maintain signal integrity and they easily optimize critical timing paths. To avoid the signal interferences with the capacitance value of the embedded memories, these embedded memory macros or the designers usually have to add one grounded metal layer over the macro to isolate the micro. So the next point in our session, memory optimization and management, which will be discussed by my colleague Pritam Kore.
Hello friends, I am Pritam. In the previous section, we have discussed about memory technology, and in next section, we are going to discuss about memory optimization and management. Advanced VLSI techniques make both density and speed of logic manufacture processing much improved, but advanced manufacture processing of memory improves more in density and less in speed. This makes memory system become the bottleneck of the whole system performance, especially for those memory systems mainly using off-chip DRAMs. To improve memory peak bandwidth, approaches such as wider data buses, higher frequencies, double data rates, or packetized protocols are used. Another kind of approach to improve memory system performance is to host utilization of available bandwidth. This approach usually takes either or both of characteristics of memory system and the memory access behavior of application into consideration. A lot of proposals to improve bandwidth utilization are based on loop manipulations by exploiting the regularity and locality of applications memory access behavior with the characteristics of memory system. These loop manipulation include loop intercharge, reversal, skewing, splitting, merging, and padding, whereas the target memory system cover caches, scratchpad memories, and DRAMs. The first point is reordering and remapping. We briefly review two schemes, reordering and remapping, for memory access improvement. In the former approach, memory access can be statically or dynamically reordered. Unlike memory access reordering that changes the order of access data, remapping changes the position of data but keeps the access order unchanged. This may save buffers and reduce design complexity needed in recording approaches. However, in some cases, such as random access, we do need reordering schemes to get better memory bandwidth utilization. On the other hand, if the characteristics of memory access can be predetermined, remapping approaches are usually a better way to gain more efficient memory access. One point must be noted is that the DRAM access ownership of each functional unit in multi-core systems also has guarded for reasonable duration. Otherwise, the advantages of remapping are diminished. Transition reduction of memory buses. As mentioned earlier, memory access take a significant part of power consumption. Therefore, techniques to reduce this part of power dissipation are appreciated. A lot of work are investigated on the topics of reducing memory traffic or reducing memory bus activity. To reduce transition of memory buses, including data bus and address bus, coding techniques are widely investigated. Due to the high correlation between consecutive address, most coding techniques focus on address buses, especially for instruction address buses. Gray coding was proposed to minimize the transitions on the instruction address bus such that there is only one transition between two consecutive addresses. However, this coding scheme does not work well for data buses because these buses are typically not sequential. As for data buses, the bus invert coding and its variant are more applicable. In bus invert coding, for example, the total number of transitions occurring between the newly arrived data and the present data on the bus is first calculated. If this number is more than half the number of bus wires, then the data is inverted and sent on the bus. Otherwise, data is sent as is. To employ bus coding technique, several issues must be considered, that is, latency, extra control signals, power consumption overhead of chosen techniques, because the protocol of commodity memory cannot be modified. The space of practical coding schemes for memory buses is limited. Reduction in memory size. Most embedded systems have tight bounds on memory space. Various techniques therefore have been investigated to conquer these issues. Compression is one of the way of reducing memory footprint. Note that if used correctly, compression can also improve the execution cycle and reduce power consumption, as it reduces the amount of data that needs to be accessed from the memory and needs to be communicated over the bus. Furthermore, the smaller size of memory also dissipates the less power. Code compressions are widely applied to various processor architectures, including RISC, DSP, and VLIW, etc. The compression granularity also ranges extensively from an instruction, a cache line, a basic block, and a function. Most compression schemes strive to produce the smallest possible encoding of their inputs. Program compaction is stressed by an extra condition: the compacted representation itself is executable. This condition severely limits the compression technique that can be applied to compact code and consequently results in poorer compression ratios than unconstrained compression schemes can achieve. Compression on data may be subjected to different constraints, such that a lossy compression scheme sometimes is acceptable. For example, lossy compression for recompressing the reconstructed reference frames are acceptable for maintaining the random access capability of motion compensated video coding schemes such as MPEG-4, H.264, AVC. The trade-off among picture quality degradation, random access capability, hardware complexity for the reduction of scheme, and latency of reference data extraction should be carefully investigated. Dynamic power management. Dynamic power management can also be applied to the memory system. In addition to traditional clock gating approach, a memory segmentation scheme that reduces power by exposing idleness in memory access. Whenever a memory segment is idle, which is the duration when no useful information is stored into it. The memory segment can be put in sleep mode. Therefore, its clock can be stopped or its refresh signal can be shut down, thereby minimizing its power dissipation. Constraint aware target for memory systems. We define the constraint aware target as one in which meeting the constraint goal is a significant design consideration and in which the target modifies its behavior based on current constraint information. As for traditional target, it is shielded from detailed information of constraints or has no knowledge of constraints. Therefore, a constraint aware target aggressively meets the constraint, whereas constraint unaware targets have little improvement or even violates the optimization goals. This is all about memory technology and memory optimization and management. Thank you.